So here we've got this circuit about which we know a little tiny bit. We're trying to figure out pretty much everything else. We know the resistances. We know all the resistances, 32 ohms. So let me just label those so we can see where they are. R1 is 32 ohms. R2 is 20 ohms. R3 is 12 ohms. And R4 is 24 ohms. So I think it'll be useful to just have those listed on the diagram so we don't have to keep referring back to this paragraph. We've also got this switch, but since the switch is open, it's not really doing anything. This is not connected at the moment. In fact, let me just cover that up. Since the switch is open, this branch of the circuit doesn't even exist for our practical purposes. It's not connected. And we want to know, first of all, the equivalent resistance. So how would we find the total equivalent resistance of this entire circuit? What could we combine together here? Yeah, it looks like R2 and R3 are going to be relatively easy to combine because how are those connected? Yeah, those are in series. And in series, what can we do with the resistances? Yeah, we can just add those directly. We can say R23 equals 20 plus 12, so that'll be 32 ohms. So those two resistors together act like a single 32 ohm resistor. And that's also connected with what else in what way? Yeah, this block is connected with exactly R1 and they're parallel. So we can add the inverses there, 1 over 32 plus 1 over 32. If we try this whole thing, these are connected in parallel. So let's say R123. We'll have to take 1 over R1 plus 1 over R23 to get R1 over R equivalent. So we fill that in, we get 1 over R equivalent equals 1 over 32 plus 1 over 32 for a total of 2 over 32 or 1/16. And then we've got to invert that. So the equivalent resistance of these three together would be 16 ohms. And if you treat this whole thing as just one big resistor that's 16 ohms, how is that connected with R4? Yeah, those are in series. R123 is in series with R4. So those we can just add together, 16 plus 24, and we get that the total equivalent resistance of the whole circuit, 16 plus 24 would be 40 ohms. So the whole thing is 40 ohms. That is, this acts like just one big resistor whose resistance is 40 ohms. Any questions on that so far? And we also want to find the voltage of the battery. And we can raise up again. This does not exist. This does not exist. So we want to find the voltage of the battery. The problem is we don't actually know much about this circuit other than the resistors. What's the only other thing we know here? What's the only other piece of given information about the behavior of the circuit? Yeah, we know V3. And that should really say delta V3. Let me fill that in. Because when we're talking about voltage, what we care about is the change in voltage. The change in voltage on resistor 3 is 3 volts. In other words, resistor 3 involves a decrease of voltage from some voltage to 3 volts less than that. And we don't know exactly what that voltage is. I mean, we don't know, we don't care what the voltage is, we just care about the changes in voltage. But we can at least say that across resistor 3, this difference in voltage from here to here is a difference of 3 volts. So let's mark that down. And I'm going to mark that as negative 3 volts because a resistor is typically associated with a voltage drop. And if we know, oh shoot, I deleted the resistances. If we know the resistance, R3 is 12 ohms. If you know the resistance and voltage drop, what else can you calculate? Yeah, we can find the current. Because we know from, in general, for any resistor, delta V of any resistor is going to be negative I times R. So that means the current is going to be negative delta V over R. Why is the change negative? Anytime you've got a resistor, I mean, whether it's positive or negative really depends on which order you're subtracting. I would typically think of it as the direction current's flowing. In fact, let's go ahead and establish direction of current. From the battery, would you expect current to be flowing to the left or to the right? And why is that? Which end are we calling positive here? Yeah, in general, if it's not marked, we typically associate the longer bar with the positive and the shorter bar with the negative. So within this battery, I would treat the left side as positive and the right side as negative. Even if it's not shown in terms of positive and negative sign, assume that the longer bar is positive and the shorter bar is negative, just by convention of notation. So we should expect current to flow from the positive terminal towards the negative terminal. So that's going to look like current flowing so and through here. But then what happens when the current hits the junction? Yeah, the junction is going to split the current. So we're going to have some current going around this way and the rest of the current going this way. So it's going to split. But then as soon as it hits this other junction, it's going to join back together and just get the current through R4, which should be the same as the current through the battery. Yeah, we do know that R1 is the same voltage as R23. So what does that tell you about the amount of current? Yeah, R1 and R23, those two branches should get equal amount of current. And that's usually not the case. Usually you would expect the current to split, but not necessarily evenly. But in this case, the fact that these two branches have the same total resistance, the upper branch has 32 ohms of resistance, and the lower branch also has 32 ohms of resistance. So this is one of the rare cases where we can assume that they are equal split, that whatever current is flowing through the battery is going to split equally through these branches. Usually it wouldn't split equally. Usually whichever branch has a larger resistance gets less of the current, and whichever branch has less resistance gets more of the current. But in this case, there's no difference between the total resistance of the branches. Each one is 32 ohms. So there's no reason for one to have more than the other. So the current does split evenly here. And let me label those. Let's say the current through the battery, although the current through the battery is also the same as the current through what else? Yeah, that's the same as the current through resistor 4. So we could call that, we usually call the current through the battery I sub 0. Just keep in mind, so I'm going to call this I sub 0, just keep in mind it's the same as the current through resistor 4. And then we've also got, let's call this I1, which is going to be half of I0 in this particular case, and I2, which is also going to be half of I0 in this particular case. So usually you wouldn't want to assume that unless you know the two paths are equivalent. And we know the voltage on resistor 3, and we know its resistance. So going back to the formula for current, voltage, and resistance, Current is I2 because 2 and 3 get the same current since they're in series on the same path. So I2 equals negative. And then, oh, I was also going to talk about the negative. Someone was asking, why is delta V a negative value? If we're talking about in the direction of current, should you expect an increase or decrease in voltage as you pass through a resistor? Yeah, we should expect a decrease. In part because the current, the electricity is losing energy as it passes through the resistor. The energy is being dissipated as maybe as light if this is a light bulb, or as sound if this is a buzzer, or just as heat. So the resistor is causing the circuit to lose energy in the sense that this point before the resistor is going to be a higher voltage. And the point after the resistor is going to be a lower voltage, relatively speaking. Because current in a resistor, current always flows from the high voltage zone towards the lower voltage zone. And since we know the difference in voltage and we know the resistance, we can plug those in. We've got delta V is -3 volts. Resistance is, for just that resistor, is 12 ohms. So we divide those and we get 1/4 of an amp. So that should be current 2. Current 2 is 1/4 of an amp. Any questions on that so far? So resistor 3 gets 3 volts of voltage, which means 1/4 of an amp of current. But what else is getting 1/4 of an amp? What else has that exact same current? What else has to have the exact same current as resistor 3? Yeah, R2 has to have the same current as R3 because they're in series. In series, they automatically have the same current. And it so happens that R1 will also have the same current. It won't, in general, I wouldn't expect that. But in this particular case, the fact that these two paths have the same total resistance means they work. But yeah, we know that any resistors in series have to have the same current as each other. So we know R2 is also 1/4 of an amp, which means for R2, we know the resistance, 20 ohms, and the current, 1/4 of an amp. So we can multiply current times resistance to find what else? Yeah, we can find the voltage of resistor number 2. That's just going to be -I times R, specifically I2 times R2. That's -1/4 of an amp times the resistance, which is 20 ohms. 1/4 of 20 would be 5, so -5, and then amps times ohms is volts. So that means resistor 2 is associated with a decrease of 5 volts. In other words, the difference from this starting value to this ending value is going to be delta V equals -3 volts. Why is it 1/4 of an amp? Because we found that the current, yeah, it's in series with resistor 3. We found resistor 3 is getting 1/4 of an amp of current, and this entire path has to have the same current. Current's only going to change if you go through a split, a fork. So it looks like this one is delta V equals -5 volts. So we now know the voltage on both of these resistors. And since they're in series, we can combine them. We're going from, if we look at this in terms of going from a very high voltage to a medium voltage to a lower voltage, this path overall is associated with losing how much voltage? Yeah, losing 8 volts. What does that tell you about path R1? Right, it's got to have the same voltage drop. Because path R1 is going from the same starting point to the same ending point. So this is also going to be associated with -8 volts. So delta V for this path is also -8 volts. Any questions on that so far? And with that voltage, if we didn't already know the current through resistor 1, we could now find that by taking the same idea of voltage divided by resistance. Voltage is 8 volts. Resistance is 32 ohms. So if we divide 8 divided by 32, we get 1/4 of an amp. But that just confirms what we already suspected, which is that these are the same currents because they're equal resistances. So we've got 1/4 of an amp through resistor 1, 1/4 of an amp through resistors 2 and 3, that path. When those two currents hit this junction, what happens to them? How would you find the new current here? Yeah, we can add those together. This is just the junction rule applied to this junction. The total current flowing into this junction has to equal the total current flowing out. Current in is 1/4 of an amp plus another 1/4 of an amp. Current out has to equal that. So 1/4 plus 1/4 would be 1/2 minute. Yeah, exactly. Current in equals current out. So that's essentially just applying the loop rule to, or sorry, the junction rule to this junction. You draw this circle, or any region really, it doesn't even have to be a junction. You draw any region, the total current flowing into that region must equal the total current flowing out of that region. That's what the junction rule is all about. Current flowing in is 1/4 and another 1/4. Current flowing out has to be 1/2. So we now know the current everywhere in this entire circuit. We've got the current in each one of those branches. And we've labeled some of the voltage drops also. Let's go ahead and label the voltage drop for R4 as well. Because we know the current is 1/2 an amp. And what's the resistance?
Isn't that like the total resistance?
Looking at just R4, not the whole thing. Because we're looking at the
I was thinking current,
drop.
my bad.
It tells us the
very...
resistance, right? That was 24 ohms.
Oh.
So if we know the resistance and the current, how do we find the voltage drop?
Do we do wait, hold on.
Yeah, we can just multiply current times resistance. So 1/2 amp.
I keep forgetting like which one's divided and stuff. Sorry. Thank you.
Yeah, in general, Ohm's law is that the delta voltage for any resistor is negative current times resistance. And that's specifically the current flowing through that resistor times the resistance of that resistor. Resistor 4 is 1/2 an amp of current flowing through it, and its resistance is listed as 24 ohms. So we multiply 1/2 an amp times 24 ohms, and we should get 12, I think. So negative 12 volts is the voltage drop across resistor 4. And it looks like we now know all of the voltage drops for all the resistors in the entire circuit. We know all of the currents everywhere in the entire circuit. Looks like the only unknown left is the voltage of the battery. And I think we can find that using any loop rule. If you just take a look at some loop, like let's say we just go for a walk around the circuit. Let's say starting here and traveling along any complete loop. What stages did we pass through along that loop? Yeah, we passed through it just along this loop. We passed through resistor 1, resistor 4, and the battery. So we can say delta V of the battery plus delta V for resistor 1 plus delta V for resistor 4. And we can ignore 2 and 3 because those aren't part of the loop we just traveled around. That's a complete loop. So what do those delta V's have to add up to? Yeah, those have to add up to 0. The delta voltage of the battery is missing. But we know resistor 1 we calculated was negative 8 volts. And resistor 4 we calculated was negative 12 volts as the voltage drop. So what does the delta voltage of the battery have to be to make this work? Yeah, looks like this is a plus 20 volt battery. So that is the voltage of the battery here. And that's what we usually call epsilon or EMF. That's the voltage boost that the battery provides, which means that the negative side is going to be lower voltage and the positive side is going to be 20 volts higher than that. In fact, now that we have this, we could even label the voltage everywhere. If we just start labeling voltages, let's see if we can map out the voltage everywhere in the entire circuit. And this I find is a really useful way of understanding what's going on in a circuit. If you just start labeling voltages everywhere. Like if we just say, I usually start with, why do we only take 1 and 4? Yeah, there are several ways to do this. If you take a look at this, this loop we just drew, the loop, one possible loop is through the battery and resistor 1, resistor 4, and back to the starting point. That loop passes through the battery and resistor 1 and resistor 4, and that's it. That's a complete loop. So you only need to add together those delta voltages and set them equal to 0. Alternatively, you could go through the battery and resistor 2 and resistor 3 and resistor 4 and say that's a complete loop. So you could say delta V battery plus delta V resistor 2 plus delta V resistor 3 plus delta V resistor 4 adds up to 0. And you still get the same thing because R2 and R3 together have a voltage drop of -8 volts. And that's the same as R1's voltage drop, which is also -8 volts because they're in parallel. And yes, you could also do this in terms of the total. You could say the total, you could say that delta V battery plus negative current 0 times resistance total equals 0. So you could also use that using the current 0, the half an amp, and R total, which was 40. So half an amp times 40 ohms is also 20 volts. So either way would work there. So let's try mapping out the voltages we have here. Starting with, I usually just start with the point right before the battery and call that 0 volts. Because we know that the point right before the battery is probably going to be the lowest voltage in the entire system. So I'll just call that 0, because that way everything else will be positive. Of course, it's not just that location right before the battery, it's this entire zone. Because anytime you're talking about points connected by just wire, all those points have to be at the same voltage. So this entire region is V equals 0. So we're labeling this entire region to be 0 volts. But then we go through the battery and what happens to voltage? What would be the voltage? Yeah, the voltage is going to increase. And specifically, it'll increase by 20 because that's the voltage of this battery. That's the EMF or electromotive force. So that means this point, and not this point, but every point connected by just wire, this entire region, up until we hit something else, such as a resistor, this entire region is all at positive 20 volts. Because you start at 0, you go through the battery, that adds 20 to your voltage. So the voltage of this entire region, this entire zone is 20 volts. And then we go through some resistors. Let's take those one at a time. Like R1, for instance, involves how much drop of voltage, how much voltage decrease. Yeah, R1 should involve a decrease of -8 volts. If we started at 20 and we lose 8 volts, what are we left with? Yeah, so that means this zone, not just this point, but this entire zone, all has to be at 12 volts. So this entire region is all 12 volts. And note that if we go through R4, R4 involves losing -12 volts. So we're going from 12 volts, lose 12 volts, and we're back to 0. So that all fits together. The one voltage we haven't really looked at yet is this one point between resistor 2 and resistor 3. So let's fill that in as well. If we're looking at the point directly between those resistors, if you start at 20 and then going through resistor 2, you lose 5. So how much is left? Yeah, exactly. 15 volts. And then going through R3, you lose another 3 volts. So you're back to 12, which matches exactly what we see over here. So by filling that in, we have now labeled the voltage everywhere in the entire system. V equals 15 volts. And note that for every single resistor in the system, current is flowing from the higher voltage towards the lower voltage. Like resistor 1, we're looking at current flowing from a 20 volt region to a 12 volt region. Current's flowing in the decreasing voltage direction. Or resistor 2, for instance. We're talking about going from 20 volts to 15 volts, and then from 15 volts to 12 volts. Or from resistor 4, we're going from 12 volts as a starting value to 0 volts. Again, current's flowing from the high voltage zone towards the low voltage zone locally. And that's true for any resistor. The current's flowing from a high voltage zone towards a lower voltage zone. And we now know the voltage at every single location in the entire system and the current through every path. Any questions on that so far? All right, and then part C is asking what changes if we close the switch, because we've had this switch here all along. Let me reveal that. The big drastic reveal is that all along there was this switch hiding here. And now we are going to open up that or close that switch. The switch has been open, meaning that nothing can flow through this. This is a broken wire. But now we're going to close this and allow current to flow. So let me set aside what we've done so far so we can come back and compare it later. Everything we've had so far, I'm going to set aside because that's all going to change. When we close the switch, let me actually draw that in. We close the switch in the sense that we take this bar and flex it over to here. Now these are connected. And what happens if these are connected? Any 2 points connected by wire, what do you know about those points?
Wouldn't R2 be shorted out or something?
Yes, R2 is shorted out because we can actually see this from the idea of voltage again. If we try mapping out voltage in the same way we already did, let's say we still call the point right before the battery 0. So we're still calling this region 0 volts. And we'll still call the region directly to the left of the battery, right at the positive terminal, 20 volts, because we're still boosting it by 20. But let's see how that voltage maps out. If we draw the voltage everywhere in this region, this location is, let me use a different color there. This location is 20 volts. And so are all these locations. These are all 20 volts. But also, because of this extra wire, this region is also at 20 volts. This entire region is now all at 20 volts. So we've got 20 volts here and 20 volts here. Which means if this entire region is at 20 volts, what's the difference in voltage across resistor 2? Yeah, resistor 2 now has no voltage difference. Because the beginning of resistor 2 is 20 volts, the other end of resistor 2 is also 20 volts, no difference. The voltage is 20 volts, but the difference in voltage would be 0. Because difference is about looking at final value and initial value and comparing them. And if a resistor has no delta V, what does that tell you about that resistor?
Shorted out.
Yeah, this is shorted out, no current at all. In the sense that delta V for a resistor is negative IR. If the voltage is 0, that tells you the current is also 0. Exactly. This is the reason why a resistor is shorted out if there's no difference in voltage. By putting in this extra path, we are linking the beginning and end. In general, if you can draw out a complete path from one side of the resistor all the way to the other side of the resistor through just wire. Those 2 points are linked by just wire, therefore they have to be at the same voltage. No difference in voltage across the resistor means no current flowing. So this is shorted out. And this alternate path that I just drew, this path from one end to the other through just wire, that's the short we're talking about in the sense of a shortcut. There's a shortcut that bypasses resistor 2 entirely. You could also even think of resistor 2 as being in parallel with this wire. If they're in parallel, then they have to have the same delta V, and just wire has no delta V at all. So we can now ignore resistor 2. Resistor 2, for practical purposes, does not exist. Because there's no current flowing through it, it's impossible for current to flow through resistor 2 because there's no delta V. So we can just treat it as not part of the system at all. We can just ignore resistor 2 entirely. What does that tell us about resistors 1 and 3? Yeah, we can't say R1 is shorted out because we can't, and if you're not sure, you can always try drawing a path. If you can draw, like we were able to say resistor 2 is shorted out because we can draw this path linking the beginning and end going through just wire. But if you try that for resistor 1, sorry, what was that?
No, I was just wondering if we can say delta V1 and delta V3 would be the same because now they're in parallel.
Exactly. R1 and R3 are now in parallel. So they have to have the same delta V. And what I was saying was we can't say R1 is shorted out because if you start before R1, there's no way you can draw a path, no matter which direction you go, you're going to hit something else. There's no way you can draw a path to the other end of R1 without going through something else. In other words, some other voltage difference. But yeah, let's take a look at voltages. We know we've got a 20 volt zone before R1 and R3. But note that R1 and R3 both start at the same high voltage zone, the same 20 volts. And then in between, or afterwards, I mean, after R1, we've got some medium voltage, but that's linked to right after R3. So this in-between zone is just one single voltage, somewhere between 20 and 0. And it looks like R1 and R3 are both starting at the same high voltage, and they're both ending at the same medium voltage. So they have to have the same delta voltage. And you could also describe them as in parallel because they're both paths that start at the same point and end at the same point. With R2 gone, R1 and R3 are in parallel. So we know they have the same voltage. And we could just use the same sort of equations we were using earlier to figure out what is that voltage, how fast is that current flowing. And yes, we can also say using the junction rule, if we actually label these currents. We've got current flowing through R1. We've also got current flowing through R3. Those currents have to add up to the current flowing through R4 and the battery. So we still have three currents here. We may as well label those I1, I3, and let's say I4. And we still have I1 plus I3 has to equal I4 because of the junction rule. But the values of those currents are going to be different than they were in the original one. We could go through the same equations and calculate what those currents are. The only problem is that takes a while. And question C here is asking a whole bunch of, if the switch is closed, which of these quantities are changing? And ideally, we'd like to be able to conceptually figure out whether these are changing or not and how they're changing without having to go through all the equations. So let's see if we can figure out any of these values without actually doing more calculations. First of all, just looking at the ideas we're looking for here, the voltages across several of the resistors, the current, well, first of all, current through R2 is going to be what? Yeah, we get no current through R2 because it's shorted out. So the order of these is a little bit confusing. I would start with this one. The current through R2 we know has to be 0. The other ones, voltage across R1, voltage across R3, voltage across R4. Let's see if we can investigate individually how each one of those has changed. First of all, by shorting this out, what exactly would you expect to happen to the total resistance? Yeah, if we short this out, we're making it easier for current to flow. And you could think of that as by removing R2, this branch now has weaker resistance. You could also think of it as adding in an extra path. Adding in extra paths in parallel always reduces the total resistance. So yeah, we've got definitely lower resistance total than before. Total resistance has decreased drastically. What would that suggest about the current flowing through the battery? Right, current through battery and R4 is going to be faster. Total resistance has decreased. It's easier for current to flow, so we should expect the battery's current to be stronger. And that is the same as the current through resistor 4. So I4 is larger, is greater than before. But what we care about, what this question is actually asking about, is the voltage. If current 4 is greater than it was before, what does that suggest about the voltage drop of R4? The delta V. How are those related? If you've got, if we go back to the idea of delta V for the resistor is negative IR. And I think this is really talking about magnitude. So technically it is a lesser value. But when we just talk about the voltage across a resistor, that usually means the magnitude of the voltage difference. So I would think of it as a larger drop. Yeah, delta V equals, formally it's delta V equals negative IR. We often just phrase that as V equals IR, but the V really means delta V, because what we care about is the difference in voltage. And since the resistor 4 is getting a larger current than it was before, but the same resistance, it means it's getting a larger voltage drop. So resistor 4 is getting a larger voltage drop than it was before. Resistor 4 gets more delta V than it did, because it's got more current flowing through it and therefore a larger voltage drop. What does that suggest about, let's say, R1? Yeah, that's going to be smaller. And we can do this with the loop rule again. If we go back to the idea of drawing out a loop, specifically, let's say we look at a loop through the battery, resistor 1, and resistor 4. That's a complete loop, so their voltages all have to add up to 0. So delta V battery plus delta V resistor 1 plus delta V resistor 4 has to add up to 0. Delta V of the battery is still the same constant 20 volts. But what has happened to delta V for resistor 4? Yeah, that has increased. So what has to happen to resistor 1's voltage to balance that out? Yeah, resistor 1 is getting less voltage. If resistor 4 is getting more of the voltage from the battery, more of the 20 volts available, resistor 1 has less voltage available. Notice that previously we had resistor 1 was 8 volts, resistor 2 was 12, or resistor 4 was 12 volts, 8 and 12 making up the 20 volts total. But now resistor 4 is getting more than 12 volts, so that means there's less than 8 volts available for resistor 1. So resistor 1 is getting less voltage than it did. So resistor, if these are light bulbs, resistor 4 has gotten brighter, resistor 1 has gotten dimmer, And resistor 2 has just gone dark completely. Any thoughts on resistor 3? What would you expect to happen to resistor 3 here when we close that switch? Let's check. Increase, doesn't change, increase. It might be useful to, well, what do we know about how I1, I3, and I4 are related to each other? Yeah, going back to the junction rule, I1 plus I3 has to equal I4. So we know that I4 has increased, but I1 has decreased. It's getting less voltage and therefore less current than it did before. So if I1 has decreased and I4 has increased, what has to happen to I3? Yeah, I3 has to increase to balance that out. So it looks like resistor 3 is going to get much brighter. Resistor 2, or if these are light bulbs again, resistor 2 goes dark completely, resistor 1 gets a little bit dimmer, resistor 4 gets brighter, and resistor 3 gets much brighter. And overall, there's more current flowing through the battery. The battery's power output has increased because it's facing less resistance, so it's easier for current to flow. Any questions on that so far? And you could also look at that kind of more conceptually. If you take a look at the branch that R2 and R3 were in, that branch is getting less voltage than it did before because R4 is getting more of the voltage. But even though the branch is getting less voltage, R2 is no longer taking up any of it. R3 is now getting all the voltage from that branch, and that's still more than the voltage R4 was or R3 was getting earlier. Delta V, in terms of this one, it was specifically asking about what happens to the delta V across each one of those resistors. Has the voltage increased or decreased? And voltage, we don't really care about the value of voltage. Delta voltage is the important thing. That any resistor, any battery, any capacitor is associated with a difference in voltage from one side to the other. For instance, the battery provides a constant boost in voltage, plus 20 volts or whatever it is all the time. A resistor provides a drop in voltage that's proportional to how fast the current is flowing, and a capacitor provides a difference in voltage proportional to how much charge is stored on it. Any other questions on the circuit? You're welcome.
So you said R3, did you say it increases or decreases?
Resistor 3 is getting more current than before.
More
because
current.
again, going back to the junction rule, current 1 plus current 3 must equal current 4.
Right.
We know that current 4 has increased because of the easier flow. Current 1 has decreased because it's getting less voltage than it did before. So if we've got an increase plus something equal, sorry, if a decrease plus something equals an increase, that missing something has to be a pretty large increase.
Makes sense. Thank you.
Mm-hmm. Any other questions on that one? All right, let's take a look at the kinematics question on this also. The person dropping off of the building, I think question 7. And yeah, question 8, that's the one with the muscles. Yeah, let's try those out. And if there's other ones out not on this test you want me to try out, please put those in the chat as files and we'll take a look. All right, so dropping off the 3rd story window, positioned a cushion below, and the person drops off the window ledge, falls for 1.5 seconds before contacting the cushion, and then a person comes to a stop 0.3 seconds later. So let's draw out a timeline here. I find it useful in cases like this to draw out a timeline of the events that are happening. So on this timeline, what are the important instants in time? What's happening here? Yeah, the initial time, let's say time 0. At time 0, the person drops off the ledge or through the window. And yeah, that's going to be at some initial height. In fact, let's go ahead and also list out everything we know about these times. At time 0, height is some initial height. We don't know how high. And then do we know anything about the speed at time 0? If you're just dropping off the window ledge, what's your starting speed? Yeah, I would assume that is 0 meters per second. If it had said you were like jumping off the window ledge or pushing yourself off the window ledge or something, that would be some starting speed. But just dropping off, I would assume that that starts at 0 meters per second. Like you're holding on and you let go. And then what's another point in time we care about? Yeah, at time 1.5 seconds. What happens at, and let me list out more conceptually what's happening. Person drops off window ledge. At time 1.5 seconds, what happens? Not exactly the floor. What do you hit before the floor? Yeah, we're going to impact the cushion. Person contacts the cushion. And it's in free fall in between. So let me put that in between. From 0 to 1.5 free fall. And yeah, while we're at it, what is the acceleration during free fall? Right, -10 meters per second squared, the acceleration of gravity. So I think this is a good idea. List out what's happening at the important points in time and what's going on during the time intervals between those times. So the person impacts the cushion. Do we have a position or a velocity at that instant? Do we even know how high the cushion is or how thick it is? Yeah, the cushion is going to provide a normal force. And that's really more about the time interval, right? Because at time 1.8 seconds, what do we know happens at time 1.8 seconds? Yeah, it comes to a stop. Person's velocity is 0 meters per second. So between these, from 1.5 to 1.8, we've got this process of slowing down because of the normal force. So we are slowing down. Acceleration equals, presumably, if you're moving downwards but getting slower and slower, which direction is the acceleration? Yeah, that's going to be a positive acceleration. We don't know how much yet, but we at least know it's going to be some positive value. Also, the problem says the cushion exerts a nearly constant force, so we can assume the acceleration is constant, some unknown positive constant. Because we know the person is getting slower. If you're moving downwards but getting slower, the change is in the upwards direction. Like let's say we take a look at let's say the initial velocity is downwards and very fast. And then final is downwards but much slower. If this is initial velocity, and this is final velocity, which direction is the change? Yeah, the change would be upwards. That would be delta V. Because you take, if you think of this as adding head to tail, V initial plus delta V would equal V final. So that means the acceleration has to be in the upwards direction. In general, if an object is getting faster, that means the acceleration is in the same direction as velocity. If the object is getting slower, that means acceleration is in the opposite direction of the velocity. Yeah, also we can assume from this that the acceleration, that the net force is upwards. The only way to get a positive an upwards acceleration is to have an upwards net force, since the net force and the acceleration must be in the same direction. So we know that the person is moving down but getting slower, so that's an upwards acceleration. provided presumably by the net force. And as for the y value, let's establish a coordinate system here. Let's say we probably want to call some location 0. What do you think would be a good location to call 0 here? Sure, let's say the cushion is y equals 0. So let's say the top of the cushion is y equals 0. You start from some high positive value, you fall, you hit the cushion, you sink into the cushion, so you're going to end up at some negative y value. But let's just define the cushion to be y equals 0 meters. So that means y initial is going to be some height above the cushion. We don't know how high above cushion, but it'll be some positive. And likewise, y final is going to be at the very end. We don't know how far below the cushion, because presumably you hit the cushion surface and sink into it. We don't know how far you sink into the cushion, but it's going to be some negative value. So you're going to start at some large positive y value. You fall to y equals 0, and then fall through y equals 0 to some negative value as you compress the cushion. We just don't know how far yet. And we also don't know what impact speed you hit the cushion at. You're going to hit the cushion at some unknown speed. Solving for delta y, yeah, we should be able to figure that out using the kinematic equations. In fact, let's try that. I guess we kind of finished off the timeline I was talking about. I may as well fill that in. We've got 15 or 1.5 and 1.8. So we can come back to those values later as needed. 1.5 seconds, 1.8 seconds. And yeah, let's see if we can get some values here. We know we're going to be going from, let's say, from the window ledge to the cushion. We know it takes 1.5 seconds. And we know the final speed. We know the final height, 0. We know the initial speed. We don't know the initial height, but we do know the acceleration. So how can we figure that out? What kinematic equation might be useful here if we are dealing with a change in height, change in speed, some time passing, and we know the acceleration? We can always start from acceleration equals derivative of speed, right? Acceleration is the derivative of velocity, and we know the acceleration is constant. So if you know the acceleration is the derivative of speed, how would you isolate speed here? How would you get v by itself? What's the opposite of a derivative? Yeah, we could take the integral of acceleration. If acceleration is the derivative of speed, then speed is the integral of acceleration. And we're assuming acceleration is constant. This is really the key to the entire idea of all the kinematic equations, assuming constant acceleration. So what's the integral of A? Well, the value of A is -10 in this case. But in general, if you integrate a constant with respect to t, what would you get? Yeah, or more generally, a times t. If you integrate a constant, because the constant can be pulled out of the integral. Any constant multiplier can be pulled out of an integral, so we just get a times integral dt. And integral dt literally just means summation. That stylized s just stands for summation. dt means tiny bit of time. D means tiny piece of. So this literally just means the summation of all the tiny bits of time. You add up all the tiny bits of time, you get the total amount of time, a times t. And formally, that's just how much the velocity is changing. This is an indefinite integral, so we also want plus some constant. In other words, speed equals acceleration times time plus a constant. And what would you expect that constant to represent? Yeah, that's the initial speed. Because if you were to plug in 0 for time, let's say you plug in 0 for time, A times 0 is 0. So that means this constant is the speed, specifically the speed at time 0. And a very useful way to think of this, v initial is the starting speed. A times t, if you multiply acceleration times t, take a look at the units there. What's acceleration measured in? Yeah, acceleration is meters per second squared. We're multiplying that by time, which is seconds. So what would you get? Yeah, meters per second, which is a speed. Acceleration times time is a speed, or rather a change in speed, change in velocity. So all this is saying is your starting velocity, why what? If you actually multiply out the units, if you have meters per second squared, and you multiply by seconds, one of the seconds cancels out. So you're left with meters per second. So acceleration times time is units of meters per second and represents a change in speed. In fact, you could even think of that as acceleration is delta v over delta t. Acceleration times change in time equals change in speed. So the acceleration times how much time has passed tells you how much the speed changes during that time. So all this is really saying is your starting speed plus your change in speed because you're accelerating equals your final speed. We can also take this a step further because velocity is the derivative of position. So how would you get rid of that derivative? Opposite of a derivative is what? Yeah, we can integrate again. Integrate both sides with respect to t. And that'll give us a formula for position. On the left side, integral and derivative cancel out. We're left with just y. On the right side, we're integrating, first of all, we can split this up, integral of at plus integral of v initial, which is a constant. Integral of at, first of all, a is a constant multiplier, so we can pull that out. Anyone remember integral of t with respect to t? Yeah, that's t squared, but also what else do we need to make it work out right? We are going to want a plus c at the end, but for the t squared, the thing is integral is supposed to be the reverse of a derivative. What's the derivative of t squared? Yeah, we need it divided by 2 because t squared would become 2t. We don't want 2t, we just want t. So we need to divide it by 2 there. Yeah, and then v initial, that's just a constant. What's the integral of a constant with respect to t? Yeah, that'll just be v initial times time. And then as before, we can find this constant by plugging in 0 for t. You plug in 0 for t and all this goes away. So we're left with just this constant is the position, exactly, position at time 0, initial position. So there's our other kinematic equation that's going to be useful here. And notice that all of this comes directly from just integrating the starting point. We start with the idea that acceleration is a constant, integrate that to get a formula for velocity, then integrate that again to get a formula for position. And this is really what the kinematic equations is all about. We've got formulas relating how velocities are related to each other before and after, how positions are related to each other before and after. And of course, you can replace y with x also. If you wanted to talk about horizontal position or vertical position, it's the same equations. You'd just be using specifically the x component of the acceleration, the x component of the initial velocity, and the initial x position. But in this case, we're talking about one-dimensional motion, just an object falling straight down. So we don't need to worry about coordinates or components. There's also one more that's sometimes useful. And I'm not going to go through the full derivation, but if you isolate time in this equation, if you solve this for time and then plug that in for time in this equation, you get another equation that's often useful. And that is, if I remember correctly, v final squared equals v initial squared plus 2 times acceleration times delta position. This is basically just what you get if you combine these equations by solving for time and substituting it in to get an equation that doesn't rely on time at all. This is often useful because it compares how fast you're going before and how fast you're going after to the acceleration and how far you travel. So this is tremendously useful if you have something like, let's say you've got a road and you know how fast the car is going at the beginning and how much it can accelerate, and you want to know how fast it's going at the end. This allows you to figure that out just based on how long the road is without having to worry about how much time passes. This is the time-independent kinematic equation. Time-independent meaning time doesn't show up in the equation at all. So this is very useful if you don't know how much time a process takes and you don't care how much time a process takes. If you just want to relate the changing speed to how far the object has traveled, this can be very useful. Still the same overall information. This is just algebraically determined by combining these equations, but it's a usefully different way of writing the information. And these 3 equations together, these are all called kinematic equations, and they can all be used in any situation where you know the acceleration is constant. If the acceleration is constant for some period of time, these are all going to be true. If the acceleration changes, these won't be true. Any other questions on that so far? And in general, I would definitely recommend knowing how to derive these from scratch. Just the idea of start with acceleration equals a constant, take the integral again. But also it's good to have these ones that I've boxed, these 3 really, just on instant recall memorization, just because they show up all over the place anytime you're dealing with constant acceleration. And it's worthwhile to just look at a constant acceleration problem and immediately know, oh, I can use these 3 equations rather than having to take the time to rederive it from scratch. So let's try that out. In this case, we know a starting speed. We don't know an ending speed, but we do know how much time it takes. We know an ending position. We don't know the starting position. Can you choose one of these equations that would relate those quantities together? The velocity equation. So of those quantities, we know the acceleration, we know how much time it takes. Do we know the starting speed and the ending speed? Let's try that. I think we could use that one. I mean, that's not going to be useful for finding the height, the starting height, but I think we could use that for finding what other information. Yeah, or v final, yeah, the velocity of the impact. So let's try that. Speed equals acceleration times time plus v initial. We end with, so if we're talking about the interval of time from the drop to hitting the cushion. So let's say from 0 seconds to 1.5 seconds. The v final is speed of the impact. Acceleration is -10 meters per second squared. Time is 1.5 seconds, and initial velocity is 0. So we combine those together. Speed of the impact would be what? -10 times 1.5. So that'll be what? Yeah, negative 15. And then for the units, we've got seconds squared in the denominator. Yeah, seconds partially cancels out, so we get meters per second. And then plus 0 seconds doesn't change anything. So that's the speed of the impact. We now know that the speed of the impact is going to be 15 or negative 15 meters per second. Speed of the impact, negative 15 meters per second. And that's useful. We can use that to figure out other information for the next period of time as well. But let's also figure out how high the building was. Because if we use the other equation for that same period of time, also we can say that y equals a times t squared divided by 2 plus v initial times t plus y initial. What's the final height? If we're talking about the same time interval from 0 to 1.5, yeah, final height is 0. Because we're assuming that by the time you get to 1.5 seconds, you've reached the cushion, which is the height we're calling height 0. Beyond that, you'll be compressing the cushion and going into the negatives. Acceleration during that period of time is 10 meters per second squared times time squared. So that'll be 1.5 seconds squared divided by 2. What's the initial velocity? Yeah, we start at 0. So 0 times 1.5 seconds is still just 0, plus y initial, the height of the building that we don't know. So we get 0 equals negative 10, and then 1.5 squared should be 2.25. So negative 10 times 2.25. We've got meters per second squared, and then we've got seconds squared, so that just becomes meters. And then if you solve that, actually, what is 10 times the 2.25 going to be?
I think we forgot to divide 1.5 squared by 2.
Oh, that's right. We got that divided by 2 there. Thank you. So we got 10 times 2.25 divided by 2. What's that going to be?
1.125.
Yeah. And yeah, then we're multiplying by 10, so negative 10, so we get negative 11.25 meters plus y initial. Solve that for y initial, we get positive 11.25 meters. So that should be the height of the third floor window, 11.25 meters, which means we can now fill that in. Now we do know how high above the cushion. And that is specifically 11.25 meters. So we now do have that information. Any questions on that so far? And is there anything else we still don't know yet? Anything else we still need to figure out? Yeah, y final at the very end, you have sunk into the cushion some unknown distance. And we want to know how far do you sink into the cushion. So let's take a look at that time interval, just the time interval from 1.5 to 1.8. So trying that from 1.5 seconds to 1.8 seconds. We know y initial is 0. Y final equals some unknown depth below 0. V initial is V impact, which is negative 15 meters per second. V final, we know that the person comes to a complete stop. And do we know the acceleration during that period of time? We do not. That's still unknown. We don't know how much time it takes, though. It takes delta t is from 1.5 to 1.8. That'll be 0.3 seconds. Yeah, so we're missing two pieces of information. We don't know how deep you sink into the cushion. We don't know the acceleration, but it looks like we know everything else. So what equation could we use to figure out those unknowns? Yeah, you could think of it as a system of equations in the sense that we know all three of these equations should be true. It's really just a matter of choosing which equations are going to be useful. And yeah, let's try that V equation. And the reason I think that one's going to be useful, we know both of the velocities. We know the starting velocity and ending velocity, and we know how much time it takes. So that means there's only one unknown. And I think that's often a good starting point. See if you can find an equation that only involves one unknown and you know everything else in the equation. Considering everything that you know about that time interval and everything you don't know as well. So let's try that. We know that V equals A times T plus V initial. V final is 0. Acceleration is unknown, but the amount of time it takes is 0.3 seconds. And the T in this equation should really be interpreted as the amount of time between V initial and V final. Plus V initial, which was negative 15 meters per second. So can you solve that for acceleration? Yeah, acceleration is going to be 15 divided by 0.3. 15 is the same as 3/10, so this is going to be times 10 thirds. Yeah, that should just be 50 meters per second squared. So that's the acceleration. And note that that's positive because it's an upwards acceleration. We've got a downwards velocity, but it's getting slower and slower and slower. So that's an upwards change. So we now know the acceleration. During that period of time, the acceleration, during the slowing down process, during the impact with the cushion, the acceleration is positive 50 meters per second squared. So we have that information now, positive 50 meters per second squared. And so the only unknown left is, looks like we're still missing Y final, how deep you sink into the cushion. So we could try the other one. Acceleration is opposite to the velocity because the object is slowing down. In general, if the acceleration and velocity are in the same direction, then the object is getting faster. If the acceleration is opposite to the velocity, then the object is getting slower. Because acceleration represents the rate of change in velocity. A change in the direction it's already moving means an increase. A change opposite to the direction it's already moving means a decrease. And a sideways change, like let's say you've got velocity going in one direction and acceleration perpendicular to the velocity. What would a perpendicular acceleration do to the object's motion? It still accelerates. It's just not changing the speed. But what would it change instead? Yeah, an acceleration, presumably caused by a net force perpendicular to the velocity, is going to change the direction of travel. Like let's say you're heading to the north and you experience a force upwards. That's going to cause your path to curve, so you're now traveling up into the north instead of just straight to the north. In this case, though, it's a one-dimensional problem. So we only have straight up and down. There's no side-to-side forces. But let's see if we can find that missing Y final, how deep you sink into the cushion. For that one, we'd probably want to use the Y equals all this stuff equation. Because we know we're missing the Y final, but we have Y initial, we have speed initial, the speed of impact. We know acceleration during that period of time. We just found that. And we know how much time it takes. So let's try that out as well. We have Y final equals acceleration times time squared over 2 plus V initial times time plus Y initial. And if we start filling those in, during this process, during the cushion process, acceleration is positive 50. Time is 0.3 seconds. Initial velocity, and in this case, we actually have an initial velocity. The impact velocity, acceleration. Oh, during free fall, acceleration is just acceleration of gravity. So if you've got an object in free fall, if the only force acting on it is gravity, then acceleration should be more formally negative 9.81, but we can round it off to negative 10 meters per second squared on Earth. On other planets, of course, it would be a different value. Also, during the impact with the cushion process from 1.5 to 1.8 seconds, that's acceleration is positive 50, but also we started with an impact velocity of negative 15 times time, which is also 0.3 seconds. And then y initial, the first impact with the cushion was at 0 meters. So I think this expression should tell us the final height that we need. So 50 times 0.3 squared would be 0.09. Negative 15 times 0.3. And then 0. 50 times 0.09 would be 4.5. And then 15 times 0.3 would be 5. I keep forgetting that divided by 2. Thank you. So that'll be 2.25. And then 15 times 0.3 is 4.5. So 2.25 minus 4.5 would be negative 2.25 meters. So that would be y final. That's how deeply you sink into the cushion. So that has to be a very thick cushion, like taller than a person. Unless you're a very tall person. So I think that gives us everything. We now know, we do know how far below the cushion, that is 2.25 meters below the top of the cushion. So the cushion has to have 2.25 meters of space to compress. And the window ledge is presumably 11.25 meters above the top of the cushion. Any questions on that so far? So with all that information, let's see if we can put together the graphs. Let me move these aside for now. So making the graphs, we're basically going to be making 3 graphs: position versus time, velocity versus time, and acceleration versus time. As you're making these graphs, let's say we just start with this as the velocity graph or position graph. So time versus, and the position here ranges from between what values? What's the highest and lowest position we should include? Yeah, it's as high as 11.25 and as low as what? Exactly, initial and final values. And I would recommend also taking a look at in between. Like if maybe it starts really low and then goes really high and then goes really low again. You don't want to look at just the initial and final values, but also consider whether there's any higher or lower points in between. So keep watch for what's the highest it gets, what's the lowest it gets, in order to choose your range. Basically, you just want to make a graph that's going to fit all of the important information. So let's say this graph goes as high as 11.25 and as low as negative 2.25. So let me mark those. And this is not necessarily to scale, but the labels are really the important thing. 11.25 meters and 2.25 meters, or negative 2.25 meters. So that will be our y-axis. And then for the velocity graph, what's the highest and lowest the velocity gets here? I mean, yeah, all the velocities are Vy, the y component of velocity, because there's no side-to-side motion. But if you take a look at all the velocities gets here that we have found here, what are the highest and lowest it gets? The velocity, not acceleration. The 50 was an acceleration. So what's the largest value of velocity? Yeah, it looks like the only velocities we care about are 0, -15, and 0, and everything in between. So our velocity graph, we can really just use 0 as the highest point. We don't care about any positive velocity because the person's not moving upwards here. And then as far down as -15. So we got 0 and -15 as the values we care about. And then 1.5 seconds and 1.8 seconds as before. And then for the acceleration, it looks like we have acceleration values such as -10 and +50. So we want our acceleration graph to include -10 and +50 as the important values. So let's mark those on the graph. +50, -10. This is a velocity graph. Acceleration graph. We've got +50 meters per second squared and -10 meters per second squared. So that lists out all the important values of all the variables. And then we can try graphing what it looks like in between those. Let me mark these as well. 1.5 seconds, 1.8 seconds. So for the graphs here, we may as well start by listing all of the data points we know at 0, 1.5, and 1.8. For instance, position starts at 11.25. And hits 0 at time 1.5 and hits -2.25 at time 1.8. So we know it hits those values. Velocity, on the other hand, starts at -15. No, starts at 0, reaches -15 by the time we get to 1.5 seconds, and reaches 0 again by the time we get to 1.8 seconds. And acceleration, for acceleration, we really know more about ranges of values rather than in specific times. We know the acceleration is, looks like the acceleration is -10 for the entire free fall interval from 0 to 1.5. So this entire interval, we've got -10 as the acceleration. And then during the impact, is it? Yeah, it's about right. It's about level. I'll make it a little higher. And then during the 1.5 to 1.8 second interval, we know the acceleration is 50 that entire time. Oh, also after coming to a complete stop, what should we expect the acceleration to be? Yeah, once you come to a complete stop, you fall, you hit the cushion slows you down, brings you to a stop. Presumably you just stay there. So I would expect the acceleration to go to 0, no further change. And let's see if we can draw out the other graphs. For velocity, how would you expect the velocity graph to look? If the acceleration is constant, what does that tell you about the velocity graph? Yeah, velocity graph should be linear because acceleration tells you the slope of the velocity graph, the rate of change. If the acceleration's value is constant, then the velocity's slope will be constant. constant acceleration of -10 means velocity has a constant slope of -10. And a constant slope means a straight line. Then during the next interval of time, acceleration has a large positive constant value. So velocity has a large positive constant slope. And notice that this, we've got a negative slope velocity corresponding to a negative value for acceleration, and then suddenly switch to a much steeper positive slope for velocity, which means a much larger positive value for acceleration. And then no acceleration, which means velocity is just going to be staying constant. No further change. What about for the position graph? If the velocity is changing, what does that suggest about the graph of position? Yeah, going back to the idea of an integral, you integrate a constant, you get a linear function. You integrate a linear function, you get a quadratic. So this should be a parabola. We should expect, or really it should be two parabolas joined together. We're going to have a parabola for the first 1.5 seconds joined with a different parabola for the next 0.3 seconds. So let's see if we can sketch out what we know about this. We know at least that at time 0, we have 0 velocity. So the position is going to have 0 slope. This is going to have to be flat at that instant. Also at 1.8 seconds, we have 0 velocity. So we have 0 slope. Let me actually draw those as true flat lines. And this is a good thing to watch for, I would say. Anytime you know that the velocity is constant, sorry, not constant, anytime the velocity reaches 0, at that instant, the position graph has 0 slope, which presumably is going to be a max or a min. It's going to come to a stop at that instant. Whereas at 1.5 seconds, we've got a very large negative velocity. So it's going to be a very steep negative slope. And then in between, we're starting with 0 velocity, then it gets a little bit negative. So the position graph is going to be a little bit steep negative slope, and then more steep and more steep and more steep. We should expect the slope to get more and more steep because velocity becomes more and more negative. But then after 1.5 seconds, during the next time interval, velocity starts really negative and then becomes rapidly approaching 0. So it rapidly becomes less steep. Something like that. So joining those together with more of a smooth curve, I would expect the position graph to look something like this. And each one of these is a portion of a parabola. We've got this very wide, broad, gently curving parabola opening downwards. And then we switch to an upwards opening, much steeper parabola. And note that that corresponds to acceleration. Acceleration is the second derivative. Acceleration is the second derivative of position. What does the second derivative of a function tell you about the function? Like for instance, if you know the second derivative is negative, or if you know the second derivative is positive. Yeah, this is exactly the concavity. If the acceleration, if the second derivative of a function is negative, that function is concave down. If the second derivative is positive, that function is concave up. So in the entire first 1.5 seconds, that graph is concave down because the second derivative is negative. For the next 0.3 seconds, the graph is concave up because the second derivative, that is the acceleration, is positive. So this is one of the things you can figure out from the acceleration. Acceleration being any negative value means the position graph is concave down during that time period. Acceleration being any positive value means the position graph is concave up during that time period. And then after 1.8 seconds, we've got no acceleration, which means no change in velocity, which means the position graph is just going to be straight line. So I'd expect the graph to look something like this. A portion of a downwards opening parabola then a portion of an upwards opening steeper parabola, and then flat. Representing the fact that you're falling, getting faster and faster and faster, hit the cushion at this inflection point where the acceleration changes, and then rapidly slow down as you sink into the cushion and then stay there. Any other questions on those graphs? All right. Anything else you want to work on? Any other question or problems you'd like to try out? Oh, I noticed several people in the Discord asking about pulleys. Would you like to try out a problem with free body diagrams involving some pulleys, just to get some practice with that? Let's try that out. And if you have a specific example you want to try out, let me know. Otherwise, I think I can probably just make one up. Let's just make up a situation here. Let's say we've got a tabletop and we've got a pulley mounted on the corner. So this is a side view. This is a pulley, like just a wheel mounted on a hinge or an axle here. And let's say we are dealing with let's say we've got a block here on the table, able to move around. And we have another block hanging here, connected by a rope. Let me draw in the rope there. The circle just represents a pulley wheel. So the idea is we've got this ledge on a countertop or something, and we've got a wheel mounted here, and then we've got this rope looped over the wheel, so we're using it as a pulley. So this blue stuff is meant to be a rope. You can tell because it is so amazingly well drawn. And this black wheel here is a pulley. And let's say we know the masses of these objects. Let's say these masses are, I'm going to call these M1 is, let's say, 20 kilograms, and M2 is 5 kilograms. Let's say we have this situation and everything is staying perfectly still. No motion at all. What does that immediately tell us? If everything is staying still, what do we know? Yeah, I would say net force is 0. The idea of momentum would be more if we were talking about something changing as time passes. In this case, there's the momentum of everything would be 0 because nothing's moving. So I would say if nothing's moving, we know the net force is 0. Specifically net force on every object. any object that could be moving is getting 0 net force because there's no acceleration. In fact, this would even be true if things were moving, but were not accelerating. Net force being 0 doesn't mean nothing is moving. It just means there's no changes to the velocity. So if these were both moving, but they weren't changing how fast they were moving, that would also mean that every force, all the net forces are 0. But in this case, let's assume everything's staying still. If we draw the forces for each of these objects, let's see what we can figure out. And let's look at each one of these individually. Let's say, which one of these do you think would be easier to deal with in terms of drawing out the forces? Yeah, probably mass 2, the 5 kilogram object. Because for mass 2, object 2, what are the only forces we would have to consider there? What are the only forces acting on that? Yeah, we definitely got gravity. And I would usually start with gravity. If you've got an object that has mass and is near a planet or star, I would start by just drawing in gravity. So object 2, we can just draw that as a single point. We got gravity pulling down, and yeah, tension. We should expect there to be a tension force because this is attached to what? Tension force from what? Right, from that rope or string. So we've got a downwards force from gravity. And how strong should we expect that force of gravity to be? We got to be careful here. The -10 is the acceleration of gravity. But in general, force of gravity is mass times the acceleration of gravity. Yeah, so that'll be 5 times 10, so that'll be 50 newtons. And that is, its magnitude is 50 newtons and its direction is downwards. So force of gravity on object 2 from the Earth, if we care about where this force is from, is 50 newtons in the downwards direction. But it's not falling because what else is happening? Yeah, we've got tension, which is the upwards force. Yeah, exactly, the rope holding it up. And we can expect that the force of tension is how strong? Yeah, should be the same, because what do we know about these two forces? Yeah, these are perfectly balanced. We know the net force on this object is 0 because everything is staying still. There's no acceleration. And note that these are not the equal and opposite forces that Newton's third law is talking about. These are more forces that have to add up to 0 because of Newton's first law. So it's not so much that we know the forces have to be equal and opposite, it's that we know that they have to add up to 0. And as a consequence of that, because there's only 2 of them and they add up to 0, they have to be opposite directions and equal magnitude. So that's everything we know about object 2. Let's take a look at object 1. Object 1, which again, we can just treat as a single point. If we were worried about rotation, we'd want to include torque as well, which means where the forces are located would matter. But as just a single object, and we don't really care about the rotation at all. This object is not going to rotate. It's just staying still. It might slide, but it's not going to rotate. Then what forces are acting on object 1? What would you start with? Yeah, I would start with gravity, again, because any object with mass near a planet is going to experience force of gravity. And how strong is that force of gravity here? And maybe friction. Let's take care of the other ones first and see if friction is going to be relevant. But yeah, we got a force of gravity that's 200 newtons. FG1, yeah, exactly. 10 meters per second squared times 20 kilograms, 200 newtons in the downwards direction. And I usually like to fill in forces in order based on how strongly I know that force has to be there. Like, I know there has to be a force of gravity because this is a object with mass near a planet. Also, there's a rope attached to it. We've already taken care of another force on that rope. What does the force of tension on this object, on mass 1, have to be? Yeah, this is going to experience 50 newtons of force of tension in which direction? Yeah, to the right, because the only thing a rope can do is pull. So object 1 is going to experience 50 newtons of tension to the right, because any rope is going to have the same tension all along its length. We already know that this rope is experiencing 50 newtons of tension because that's how much it has to experience to support object 2. And so that's 50 newtons everywhere along the rope. Essentially what the pulley is doing here is redirecting the force. It's bending the rope so you can get a rightwards force on one object and an upwards force on the other object. And of course, that means in order for the pulley to actually stay in place, the pulley itself is experiencing a diagonal force from the table. But we're not worried about that because we're just assuming the pulley is held in place by the tabletop. So the forces we have so far look like they are down and to the right, which means this block mass 1 should be sinking into the table and going forward to the right. But it's not doing that because what other forces are holding it in place? Yeah, presumably there is a normal force, the tabletop pushing it up to prevent it from sinking. And how strong would you expect that normal force to be? Right, that's going to be 200 newtons because we know there's no acceleration in the vertical direction. So that means the vertical components have to add up to 0. But also, these so far, I mean, the normal and gravity force will cancel out. Yeah, in order for this object to not be accelerating, we have to have a friction force as well. The friction force is essentially a reaction to the attempt of the rope to pull it forward. The rope's tension force is trying to pull up the object to the right. The only way to prevent that is for friction to be pulling it to the left. So let's fill that in. We know that there presumably should be friction to the left. And in order for this to be actually balanced, how strong would that friction force have to be? Yeah, that's going to have to be 50 newtons as well, because we're assuming that the horizontal forces also add up to 0. We're assuming there's no x direction acceleration. So that would be the complete free body diagram for both objects. And moreover, if we know the friction and the normal force, what else can we calculate? How are those quantities related? Well, we could add them all together to get the net force. But yeah, friction coefficient is going to be important here. That the coefficient of friction, usually called mu, the Greek letter mu, is really just is defined as the ratio of friction force over normal force in terms of their magnitudes, ignoring direction. The idea is that the friction force is always going to be some multiplier times the normal force, some fraction. So mu is typically going to be some value between 0 and 1 that ultimately depends on the materials of surfaces in contact. Like if you've got, for instance, maybe wood on porcelain tile, there's going to be a certain coefficient of friction of those. Or if you've got rubber tire on asphalt, that's going to be a different coefficient of friction. Or maybe, I don't know, a block of iron on ice. Let's try to figure that out. If we solve for that, friction divided by normal force, what would we get there? We've got 50 newtons of friction divided by 200 newtons of normal force. 50 over 200 reduces to what? Yeah, 0.25 or 1/4. And note that that's also unitless. Newtons and newtons cancel out. So mu is 0.25, not 0.25 something, just 0.25. So that would be the coefficient of friction that has to happen to make this work. The only way for this to be in equilibrium is for these surfaces to have a coefficient of friction of 0.25 or more. If it's less than this, then the object is going to start sliding and get faster and faster. If it's more than this, then the object just stays still. So in order to stay perfectly still, we need the coefficient of friction to be greater than or equal to 0.25. And again, that depends on the material that the surfaces are made of. Any questions on that so far?
Wait, so Casey, if it's less than, if the coefficient of friction is less than 0.25, it'll just like slip off, right? Basically.
It'll start sliding. I mean, the thing is, if it's less than 0.25, that means the force of friction won't be able to provide 50 newtons of force. So that means this system is going to start to slide. As it does so, as soon as it starts to slide, then you change from this would be called static friction if it's staying still. But if it starts to slide, then you now have kinetic friction or sliding friction, and that's going to be a different value. Typically, the coefficient of kinetic friction or sliding friction is much smaller than the coefficient of static friction. And you can see this if you're trying to push an object. Like let's say you've got an object and you're trying to push it. Getting it moving in the first place is difficult, but once it starts moving, it's much easier to keep moving because the sliding friction coefficient is much weaker than the static friction coefficient.
Thank you, Casey.
But let's say we change this so that the friction just disappeared entirely. Let's say we greased up this surface so it has almost no friction at all. Let's see what would happen there. If there's no friction at all, then we just get rid of this force entirely. Then what would you expect to happen? Yeah, this is going to slide off. And of course, it's not going to be instantaneous. We're going to get, well, let's say we start off with 0 speed, but it's going to start accelerating. Object 1 accelerates to which direction? Yeah, because we've got a net force to the right. And what about object 2? If object 1 is moving to the right, what's going to happen to object 2? Right, object 2 is in the process of falling. It's not truly free fall because the rope is holding it back, but it is going to start to accelerate downwards. And we could actually figure out how much it accelerates by analyzing the new free body diagrams without friction. And one of the interesting results of that, why were we assuming that these forces add up to 0 in the first place? On object 2, for instance. Right, it wasn't moving. In particular, it wasn't accelerating. But now the object is accelerating. We no longer have static equilibrium, so we can no longer assume these forces add up to 0. Instead of adding up to 0, we should say F net equals, what should F net equal if it is accelerating? Should equal 0 if it's not accelerating, but if it is accelerating, think back to Newton's second law. Net force equals what times what? Mass times acceleration. In general, the net force on an object equals the mass of the object, which we know is 5 kilograms, times the acceleration, which we don't know yet. We know it's going to be accelerating, presumably in the downwards direction, but we don't know how much it's accelerating. Well, let's say 5 kilograms times A downwards. Yeah, mv is momentum, ma is the rate of change in momentum, which is equal to net force. So we should assume the net force is downwards. So would you expect force of tension to be the same as gravity or stronger or weaker? Yeah, tension is going to be weaker because we no longer want the forces to add up to 0. We want them to add up to a downwards amount because we're assuming this block is going to accelerate downwards. So we should assume the tension force is weaker. And that's true of both of them because these are still going to be the same tension force as each other. We just have some unknown tension force. So let's say we want to figure that out. We want to figure out how much tension force and how much it accelerates. we don't know how much tension force, we don't know how much acceleration, but we at least know that net force has to equal 5 kilograms times the acceleration. And we can even write that out. Net force here is going to be Ft, which we don't know, plus 50 newtons downwards. Since that's downwards, let's call that negative. Actually, what might work a little better here, since we know that this is moving in this certain direction, it's often useful to treat the direction of motion as the positive direction. So let's just say we're defining this direction to be positive. And it can kind of seem counterintuitive to define downwards as the positive direction, but it's often very useful to just treat one direction as positive for the whole thing. So let's treat the direction everything's moving to the right and down as the positive direction. That way, gravity is positive and tension is negative. And that should equal mass times acceleration. So we don't know what the acceleration is. We don't know how strong tension is, but we at least know mass times acceleration equals gravity plus tension. Any questions on that so far? And then for the other object, we can also say that net force equals mass times acceleration. But for this one, what's the only force acting on this that doesn't cancel out? We were assuming friction disappeared here because we're assuming we greased up the tabletop. So yeah, tension. The normal force and gravity still cancel each other out because there's no vertical acceleration, but tension is causing a horizontal acceleration. And what's the mass of this object? Yeah, 20 kilograms. And acceleration we don't know, but we at least know this is accelerating to the right. So we've got two unknowns here. We don't know acceleration, we don't know tension, but we also have two equations. And we know that since these objects are connected by the same rope, we know they have the same F tension. They're also moving together, so they have the same acceleration. And yeah, we can just substitute. We know that tension force, this is one of the coolest things about moving text around. You can substitute by going and merge them together. So we know that the force of tension is 20 kilograms times acceleration. So let's go ahead and combine those equations together. 5 kilograms times acceleration equals 50 newtons minus force of tension, which is 20 kilograms times acceleration. And now what's the only unknown left? Yeah, acceleration. So add 20 kilograms to both sides. Divide both sides by 25, and we get, looks like 2 meters per second squared. So this whole system is accelerating at 2 meters per second squared. Notice that that is significantly slower than we'd expect from gravity. This is definitely not free fall because tension is preventing it from falling that fast. But the whole system is accelerating. Block 1 is accelerating forward at 2 meters per second squared. Block 2 is accelerating downwards at also 2 meters per second squared. Same amount of acceleration because they're connected, different directions because the pulley redirects the forces. We could also even figure out force of tension by plugging it into either of these. For instance, 20 kilograms times 2 meters per second squared would be 40. So it looks like the tension is 40 newtons in this case, which is, as we predicted, weaker than it was without friction, or weaker than it was with friction. So no friction means 40 newtons of tension in the rope, and the whole system accelerating forward and downward at 2 meters per second squared. And if you wanted, you could even use, for instance, the kinematic equations to figure out how far it travels in a certain amount of time. Or maybe if you know the distance to the pulley, you can figure out how much time it takes to reach the pulley or how fast it's going when it hits the pulley. Lots of other stuff you could figure out once you know the acceleration. Any other questions on that? All right, we are way past time, so I'm going to call it quits for the moment. But feel free to ask any other questions you'd like on Discord. I am going to have office hours tomorrow morning, 10 to noon, if you have any further questions. Best wishes on finals. Have a great summer, and I hope to see you all in Physics 7C. You're welcome.